Welcome to today's webinar. Today we will show you how you can exchange data between Revit and rFIM6. My name is Andreas Hörwold. I'm responsible for marketing and PR in the company Global Software. For instance, the German and English webinars, technical content of the website, customer projects, newsletters, and so on. I will be the moderator today and I will answer your questions together with Paul Zivelgien. The presenter will be Lukas Sühnel. He's responsible for the main responsible person for the interfaces in rFIM6, and he works also in the customer support team. Paul is also responsible for the interfaces. Yeah, and as I already said, he will help me by answering your questions. Okay, I show you how you can ask questions, at least for the attendees who participate the first time. First, I switch off my webcam that you can see the full screen. Yeah, just press that button with the question mark, then enter your question in that field, press send, and we will receive your question and we will answer you. The other way is to watch the entire webinar and then email your questions to info@global.com. Okay, that's at the moment all from my side. I hand over to Lukas. Lukas, it's your turn.
Thank you very much for the introduction, Andreas. I will continue with the content. I have 7 chapters. I want to start with the introduction of the Revit model that I created for that webinar. Afterwards, I want to show the creation of the analytical model in Revit this time. So showing how it could be done using Revit 2025. And then I want to introduce our Global plugin in Revit to run the export to rFIM6. In chapter 4, I want to mention the following steps in rFIM6 that should be done ideally to check the model and run some model adjustments. And the last chapter from this first big topic is the import from rFIM6 to Revit. So the first 5 points are related to the direct data exchange between Revit and rFIM6 using our Global plugin. And the next big chapter is the data exchange with rFIM6 via IFC. And here I also want to show our new object in rFIM6, the nodal links. With that being said, I want to start with the data exchange via Revit. Therefore, I will open my Revit model. So, as you can see, it is a regular steel structure. In that plane, I have a rigid frame. Most of the main beams are supported by additional columns. And in that view, I have mostly coupling members with a couple of bracings. Some of the joints already have been defined with an end plate and some bolts, or here you can see that the columns are connected, hinged to the beams. So some details, I just want to mention it. It will be more relevant when we create the analytical model afterwards, or when we talk about the data exchange via IFC. Yeah, that is the model, and the plan is to help the structure engineer by exporting it to rFIM6. For the export to rFIM6, we can use our Global plugin. You can see it here on the top. There are 2 icons for rFIM6 and for rSTUB 9. It's always about the export and the import. And then we have, let's say, the important one, the conversion table as an additional icon. Here you can match the material and cross-section names between rFIM6 and Revit. So if we have a look at the material here, it's a steel S235, and the name in Global is different. Therefore, I have to open the the conversion tables and assign to that Revit material name a proper RFEM material name. The same can be done for the sections. In my case, everything's already defined. So, what is necessary for the data exchange with RFEM 6 using this plugin? It is necessary that we have the analytical model in Revit. The model that we see here is the what I call physical model. Every object is represented as a solid, basically. The analytical model would be a simplified line for each of these objects. Revit can create the analytical model. It did it kind of automatically with Revit 2022 and older. With Revit 2023 and newer, for example 2025, the version I'm using here, we have to start this conversion manually, and the steps for my model is what I want to show next. Therefore, I will open an additional plan window for the analytical model. I will place them next to each other and again show the steps for the creation of the analytical model. It can be done in the Analyze tab. Here you have the analytical automation. And with my Revit version, which is a little bit of an older 2025 version, I have only two options. I have one option to convert the analytical model into a physical one. We don't need that here. And the other one is the physical to analytical generator. That's the one we are using today, or I'm using today. In newer Revit 2025 versions, or I guess also 2026, there are two options for the physical to analytical conversion. Yeah, as I said, I'm going to use this one now as it is working quite well for me. I can run this little tool, and the first thing that I have to do is I have to select my physical elements that I want to convert. So I hit the select button, select the columns, and that's it. Usually I just try it, I give it a try, yeah, how it will work with the default values, and then we can modify it afterwards. So let's have a look. We can see here the analytical model on the right hand side now. It's quite obvious that it's not ideal. There are some bends in the actual straight coupling members. Some nodes have been merged, as we can see here. That should be that is the coupling member in the wall in the front. Here, for some reason, it's slanted. So the node which should have been here has been merged with this frame joint node. So there are some additional adjustments required. And due to the fact that some nodes seems to be merged here, I will use this first tolerance setting that Revit offers me here, custom tolerance of the distance between analytical elements. Here it's set to 1 meter, and I will just make it smaller so that merging of nodes won't happen that easily. So I run it again. I don't have to select again, just change the options and run it again. And we can already see I have now these coupling members on their own level, which is nice. What's not so nice is that the coupling members in my roof are flying around. Yeah, they are not connected to the main beams. Also on my columns, I have a little bit of like cantilever left over. Actually, I want to merge the nodes from the top to the frame joints. So additional requirements, adjustments are required. And there is an option which could help. This option is called Adjust Analytical Elements to Nearest Level. What does it mean? I will already activate it. So let's have a look on the west view. Of course, I used some levels to create my structure. Yeah, usually you create the levels and then you place your objects with the, for example, set justification set to top. So whenever you place an object, the top flange will be placed on the level of, or on the plane of this level that you referred to. And what we can do is, with this option, we can move the analytical elements that are placed on different levels now, depending where the center is of that object. We can move it or project it to the nearest plane. That's an option that could help to bring my coupling members in the roof and the frame members and maybe even the frame joints here, or the ends of my columns, into one level. So let's run this. Yes, we can already see it kind of did what we expected or what we were hoping for. All the objects are now placed in one level. Now let's have a look at this 3D structure here. In general, it looks quite nice. What is not so ideal, that the analytical line for my coupling members is placed on the upper flange, and also for the main beams, all the analytical lines are placed on the top flange level. Actually, I would prefer to have them in the center of the main beams. That's what my target would be. That's what I want to achieve. And again, there is an option that could help. This option is called Consider Only Levels with Structural Parameter Checked. So let's have a look into one of the properties of the levels. So if I select the level 2 here, there is a parameter called structural, and I can activate it. So I have the chance to project my analytical objects onto levels where this parameter is checked. Obviously, it doesn't make any sense to activate it on the existing levels because this is already working now. But I could create additional levels on the height where I want to have my analytical lines projected to, and then run this conversion again. So that's what I'm going to do. I'm selecting the level. I'm copying it from the top flange location to the center of the beam. And then I will rename it. Wait. It's called -2. It's not correct. Level 1. Oops. Level 1 structural. And set the structural setting active. And the same I will do for the level 2. Copy it into the, that should be the center of the beam. Rename it to level 2 structural and activate this option. Now, when I run the set it active, consider only levels with structural parameter checked. When I run it again, I expect all these members to move downwards slightly. Yep, this happened. We can also see it here on the left hand side. The analytical line of the main beam is now in the center of the main frame beams. So that's nice. The only thing that was now modified in a not so nice way is the second row of coupling members in my walls. They also have been projected into the top level. So those are the analytical lines that should actually be placed slightly lower. So there seems to be, or there must be, a tolerance that I can modify that not all the analytical lines will be moved onto a specific structural level. And that is the tolerance under 3.2, custom tolerance of the distance to the nearest level. Here set to 1 meter. I can reduce it, and I can use again a small value to see what's happening. And if I set it quite small, then yes, we can see the analytical lines now again in the center of the coupling members, but do it to the very small tolerance. The coupling members on the top are now too far away from the analytical plane or level so that they won't be projected onto it. So I have to find the right distance for that value, for this tolerance, and 0.6 meters should be okay, exactly. Now I have the analytical model that I wanted to achieve. Yeah? My elements are placed in the center of my main beams. They are all connected. The coupling members are on their own levels. That was what I wanted to achieve here. Okay. Then let's merge these windows again. Now I can run the export to Orpheum 6. Yeah, I have my analytical model. In general, there would be more options how I can adjust it. Maybe I can quickly introduce them. So in the Analyze tab of Revit, you have additional options. You can, for example, define boundary conditions, nodal supports for points, for lines, or for areas. So you can support your structure. You can select into an element, a beam, for example, to define member end releases. Or you can define load cases and load combinations. And you can even fill these load cases with point, line, and area loads. So Revit has a basic set of analytical objects to optimize the analytical model. It is up to your decision how you want to work. If you want to have Revit as the main center BIM model and you feed all the other departments from Revit, or if it is just meant to be a simple data exchange, you want to support the structure engineer a bit, so you create the analytical model and you send it to him. So it is up to you how much information you want to pack into that model. I leave it as it is, and I want to show now the export. Therefore, I'm moving Revit to the left-hand side, Orpheum to the right-hand side, and show the export. I'm starting here the export model, or by clicking on the export model icon. I can create a new structure or overwrite the existing one. In my case, I want to create a new one, obviously, because there is nothing in Orpheum. The Z-axis should be upwards. I want to refer to the physical properties. Let me quickly explain that. So in Revit, you can select the physical object, the column, and it has a set of information, a material, a cross-section, and so on. And if you select the analytical line, you basically refer to the same object in reality, but it has its own set of information. It could be different. You can assign a different cross-section or different material to the analytical line compared to the physical object. We can refer to both property sets. So it is up to you if you want to use the physical property set or the analytical property set of information during the export. You can export only parts of the structure, either by selecting them graphically or by creating visibilities in Revit. So for example, if you want to export only one frame to Orpheum, then maybe select all the objects beforehand and then hit this button. Additionally, we can export the grid. I didn't show it, but there is a grid in Revit and I want to export it as well. And then we can also decide if we want to export load data, so the load cases and the loads that have been defined in Revit or not. Since I don't have any, I don't want to export them. And with all these settings defined, I can run the export, and now Revit and Orpheum are communicating with each other. So both programs have an API. We link these APIs, and now the communication will happen. This also means that both programs have to be installed on the same PC. So this is a requirement for using the Glubal plugin in Revit. Revit and Orpheum have to be installed on the same PC. So the export is done. Let's have a look in detail. Yeah, at first always checking visually if everything is okay. Is the rotation of the members of the columns fine? Is anything obviously not connected or something like that? That's always the first check that I'm doing. And then there are additional tools inside of RVM that can help to identify issues with the model. You can find these tools in the tool menu under model check. And an important one is the identical node check. This will not check just identical nodes. It will look if there are nodes closer as the tolerance to like placed to each other. Yeah. So if there's a node with distance smaller than 0.5 millimeter to another node, it will find this node. And obviously this tolerance is quite low. So I would use a different one here with maybe 10 centimeter, click on that button, and still it found no duplicated or identical node, or no node in a range of 10 centimeter to another node. So this tells me that in general the model should be fine. Yeah, it could happen that you get a list of nodes here because maybe the Revit analytical model was not created properly or whatever. Then this check will help you. Just to show you how it looks if it finds something, I increased the tolerance even further to 1.5 meter. And now you get a list of nodes. Here, for example, node 2, 49, and 71, also shown here with the red arrow. They are within a range of 1.5 meter. And then you can decide what you want to do with it. In my case, nothing, of course, because this is okay. But imagine you find this kind of list with a small tolerance, then you have some options how you want to treat these situations. Another check which is quite helpful and which also helped me in the preparation is the overlapping members. Here, no overlapping members have been found, which is nice. When I prepared this webinar, I for some reason modeled the bracings twice on the same location in Revit, maybe due to some copy function. So I had also two members here on top of each other. I did not see that visually, but the model check found it. So it is quite helpful to run these checks. And one of the last checks that I would run is just calculating the dead load case to see how my structure reacts. Is the deformation okay? Are the forces according to my expectations? And therefore I have to support the structure first. So create a nodal support here. Pin support, which is fine. Let's make it a bit bigger so we can see the nodal supports. All right, then there are additional settings in RVM 6 which can help to get a understanding of the structure. So now I see a lot of beams, but these beams can have different sets of information or properties. For example, I could render my structure according to my sections. So now every section, pink for some reason is shown twice. Let's use a different color. Maybe this one. Now every section gets its own color, and I can easily understand what section has been used on which location. Is it correct? Is it according to my expectation? Yes or not. Or I could check the member type. All members have the member type beam, and if I also check the hinges, there are no hinges in my structure. So currently all members are connected rigidly with each other. That means full force transmission on every joint. That's not what you want in your analytical model. Depending on the steel joint you create afterwards, or what you have as an image of how the forces should flow through your structure, you want to assign member hinges or member types, and this is what I'm going to do now. So switch the rendering to member types, then I go to my sections, and I can easily select all my bracing members by selecting the cross section first, double click on the members, and assign the tension member type. Yeah, we can also graphically see that this is now a different type. Tension member type means they have a nonlinearity, failure under compression, and they also have hinges for the bending moments on both sides. The same I can do for my coupling members, HEA 160 and 120 for the walls and the roof coupling members. I switch them to truss. So again, a type where I have no bending moment transfer on the end. Yeah, so automatically hinges on both sides. And with that, I can optimize my analytical model here. And the last thing that I want to do is I want to assign some member hinges. Let me show the Revit model again for a second. I mentioned it in the beginning, but the main beams are supported through additional columns, and I have here a hinged support or a hinged connection between them. And so at the end of my columns in the center and on the wall, I want to have a bending moment hinge. So I can create it in different ways. Let me show it this way. I create the member hinge first, and then I can assign it graphically to my members, and maybe in combination with the view IP 450 and HE 300, and I can select all of them at once. So all these columns in the wall and in the center of my building, they get this additional hinge. We can see the hinge now also. These yellow small circles. All right. So far concerning the adjustments that I want to make here. And now let's run the calculation of the dead load case. Before we do it, I have to assign the static analysis setting. It should be calculated according to a first order analysis. I run it. It automatically considers the self-weight of the structure. And then we check the deformations and forces if it looks according to our expectations. So, showing the deformations, I see nothing suspicious here. It could be that, I don't know, a beam is kind of falling down at one side or so, then you know there's a connection not modeled properly, but here everything as expected. I can check my axial forces, maybe the bending moments, to see if I have moments on those beams where I expect them. So for example, if we highlight here the main frames or main beams with the columns, we can see, this is the expected bending moment, transfer from beams to columns and so on. So the connections should be fine. Or I can also check it for the coupling members, that they have no bending moments on their ends. And also this looks fine. So these are some of the ways how you can quickly control your model and check if it is behaving as expected. Yes, this is where I want to stop here for now. What would be the next step? The next step would be creating additional load cases, assigning the loads, combining the load cases, running design add-ons. All this can be done in RFIM 6. But again, the focus should be on the data transfer today, so I'm skipping that. To round this first part up, the data exchange via the direct interface, I want to show also the import into Revit. So let's assume we have modeled something in RFIM. The structural engineer started with a project, and he wants to support the drafter or the Revit user at the end of the day. So he wants to give him some information. So therefore I'm deleting all information I had in Revit. I deleted the model, and I can run the import into Revit. And again, I can decide what information do I want to import. Do I want to import only the analytical model, so just the lines with the information about cross-section and material, or should it automatically create the physical object, or maybe both, which makes sense. So I import the analytical and the physical model here. Again, communication takes place between both programs. And it's done. So we can clearly see I have the physical model here and also the analytical model. The analytical model now also contains the supports that I assigned in RFIM. Or if I check these coupling members, I have also information about the releases, the hinges on the member ends, or on my columns, for example, on this column on the end, there's a hinge. So yeah, these informations have been shared, and also the physical model, as I showed before. Yeah, this is the Revit link. Import and export in both directions. Yeah, so far regarding that. Now, as I mentioned before a couple of times, we can only use it if Revit and RFIM are installed on the same PC. This is, of course, not always the case. Yeah, it's also often the case that the Revit user has a Revit installed and structure engineer RFIM, and then the direct link is no solution for the data exchange. So what else could we do? Well, as far as I know, but please correct me if I'm mistaken, Revit has no export format for the analytical model. So as far as I know, I cannot export the analytical model from Revit to somehow. Therefore, I have to refer to the physical model, and for the export of the physical model, I can, of course, use the IFC format. I will do it. It's no big deal. I can easily export an IFC file from Revit, and I can do it example 1, for example, and the export setup should be, for example, the IFC4 reference view. That's something we support in RFIM 6. We also support IFC 2.3 coordination view. Up to you what you want to use. Yes, so let's export this. All right, the export is done. I can open this IFC file in a viewer. Oh, sorry, I made a little mistake. Well, yeah, I used the file that I imported from RFIM to have a comparable workflow. I actually meant to export the original Revit file, where I have all these connections inside. So let's do it one more time. Export IFC desktop example 2 and reference view structural. Okay. So it's done. So this was the file I just exported, the one I imported into Revit from RFIM. That's not what I wanted to use. I want to use the original structure that we have here, including these steel joints and the screws or bolts and so on. So yeah. Okay, so that has been exported from Revit. I can show it here using the BIM Vision viewer. Quite nice to handle. You can select the object. You can see directly the cross-section. If you open that, you can also see the material. So it's doing what it should. And I can import such an IFC file also in RFIM 6. So the alternative to the direct interface that I want to show is the import or the data exchange via the IFC. Therefore, I'm closing that file that I had, and I can run the import of an IFC file via the menu. I will rotate the file during the import because usually global z-axis is up in CAD programs. In RThium, I'm using here set global z-axis down, so I have to rotate them. I can press OK, and my structure will be shown. Now, just let me activate the global coordinate system again. Let's have a quick look. We can see the content of the IFC, similar to BIM Vision. So what we see here is our IFC objects. First of all, there are no native objects. So this is not a real member. There are no sections imported. This is just a graphical object. It's basically an IFC viewer. And I can also display the information from these objects by double-clicking on them or activating the IFC property panel. So if you select one of these elements, you can see the information, the cross-section, the material should be somewhere here, and so on. Now, what can we do with it? We can convert these IFC objects into members or native data, via the context menu. We have here options to convert the selected objects into straight members, into surfaces, or into solids. Obviously, it makes sense to use members, but before we run this conversion, please make sure that in the conversion tables you have a proper conversion. The metal steel S235 needs a proper material from our own library. You don't have to do it. You can also change the settings, the properties afterwards of these objects, but I mean, it makes sense to do it beforehand. It will be saved for the future, for future exports and imports. So for future imports, then you don't have to do it again. Same for the sections. They have been converted already. Yes. So now I can select the objects that I want to convert. Before I do that, I want to make sure that I'm hiding unnecessary IFC objects. For example, these fasteners here. I could, in theory, convert them also into a member, but it doesn't make any sense. Therefore, I'm hiding these IFC entities or IFC types, slab, side, project, anything that I don't need. And I only leave IFC beam and IFC column active here. And the rest, as you can see, is now hidden. So these are the objects that I want to convert into straight members. Then it takes a second. And now I have here native data. You can also see it. I have now the sections from the IFC file. I have the members here. So now these are native RThium members. And it looks quite okay. All the objects will be placed according to the IFC file. So you can see again the coupling members, or are kind of eccentric, that they are in the same plane as the main beams. And also all other objects will be placed according to the IFC file. Again, I could use these rendering options to check if the data is correct, which is the case. So what would be the next step? The next step would be to connect the elements. Because if we have a closer look at the situation, we can see that every member is basically on its own. It's not connected at all. And now you have two options how you can deal with these situations. You could use tools from RThium to manually connect them, which is possible. For example, if we select all these coupling members in my walls, we would have the option to trim the member. We could extend it to the next member line, to both sides. And if these members and the basically columns are in one plane, they will be connected to each other. So now all these members are already connected. That is a solution for that specific case. For my coupling members here on top, it won't work because you can clearly see that there is no intersection between this main beam and the coupling members. So here you would have to do some additional modifications, for example, projecting all these members into the plane of the main beam. And then again, you could use this extend to find the intersection points. These are tools and options that you can use to manually close the gaps and connect the elements. That's, however, not what I want to show today. I want to show an alternative. And this alternative is the new object which we call nodal links. How do they work? Maybe I open the dialog for that. Nodal links are assigned to nodes. So it's basically a property of a node. And this nodal link will search starting from the selected node for nodes, members, or surfaces. And it will create a connection between the selected object via a rigid member. So it will automatically try to connect the node and other nodes or members or surfaces. I can define the search radius. Currently, we have here only the search method closest object, but maybe others could be implemented here. And I have settings to define hinges at the start or the end of the nodal link, to define a proper force transfer. And that's an option that I could use as well to close my gaps. And I will do it for that structure here today. And for that, I will create a couple, or I will use some of these visibilities that we have. So I'm displaying now the main beams and the main columns. And my goal would be to connect the beams and the columns that are currently not connected. So how can I do it? It's quite easy. I create a nodal link, assign it to the nodes of my beam, this one, or these one and these ones. And I say maybe search radius 40 centimeter. Please connect to the closest member. And that's all. And it will create these nodal links, how we call them, or rigid members, from the node to the member. And now there is a connection established. And I'm doing the same for the columns to the main beam. Therefore, let me activate these additional columns. So a new type, new nodal link. I'm assigning them to those nodes. They should look for a member close by, maybe with the radius of 0.4 meters. And speciality here is I want to create a hinge at the end of the nodal link. Now for the bending moments, as I said it before, we have here these let's say hinged connections. A bit tricky. These hinged connections. So at the end of the nodal link, I want to have a member hinge. We could argue if we want to place it on the start of the nodal link or at the end. More correct, it would be probably even at the start of the nodal link. So down here, because we have some kind of a lever arm between the lower flange to the center, but well, we simplify it a bit to avoid torsional moments. So now we also have these nodal links here. And I will simply continue. What's next? Maybe, no, not those. The coupling members in the walls. I will create a new nodal link type. Select all these nodes. Okay, search radius again. And it should look for members close by. Now let's have a look if they found or if they create proper couplings. It's looking good here, looking good here. Here something went wrong. So therefore I have to cancel the visibility mode to understand what's happening. And I can see these diagonal members, the bracing members, they interfere a bit. Yeah. From that node on, the closest member is not the column. It's actually this diagonal member. So I kind of have to remove the diagonal members from that generation. And I can do it by double clicking on this nodal link and say here exclude objects. And then I'm just selecting these bracing members, press again OK. And now it creates a proper connection again to my columns. The same can be done for the coupling members on top. So yeah, for those, they should be connected to the main beam. Let me open the rendering again. Yeah, so here I need a connection between the main beam and these coupling members. And again, I'm creating a new nodal link. I assign them to, let's see if I can do it like this. Yep, catch the right nodes. Search radius can be smaller again. Please connect to the closest member. And at the end of the rigid link, again, I want to have a hinge. Yeah, because the coupling members are connected with hinges to the main beams. We will control if it's okay. Here it looks good. Here, well, partially again. I assume it's again related to the bracing members in my roof, and yes, this is the case. They are closer to that node as the main beam. So once again, I remove the influence from my nodal or from these bracings. And now it should look quite fine. Yes. Now it's working as expected. And the last thing that I have to connect to the model are the bracings. Yeah. And concerning the bracings, I don't want to look for the closest member. I actually want them to be connected to a specific node. Yeah. To that node, for example, in the wall. So this time I create a new nodal link. Oh, sorry. A new nodal link on all these end nodes of my bracings. And I want to link them to existing nodes. Yeah, not to members, but to nodes, closest nodes. And let's see what's happening. On the bottom, it looks fine. Yeah, it catch the bottom node of my columns. Yeah, I expected issues here. Here it's not working. They are connecting to the node of that coupling member and not to the node on my column. So again, I mean, I showed it a couple times. We can use exclude object, and I can exclude the nodes from my coupling members. Just a second. Yeah. Okay. Let's have a look. Yeah. Now they are connected as expected. Yeah. They are not allowed to connect to that node anymore. So that's why they are connecting to the next closest node, basically. All right. This is an option or a way how you can connect your imported and converted analytical objects with each other, yeah, with the nodal links. And now we can do what we did before. After the Revit import, we can support the structure, adjust some settings, and then run a calculation. Let's do it quickly. So I create a nodal support here, assign them to the bottom nodes. Okay. I somehow selected this one. Yeah. this looks good. Yeah. Then we can modify again the settings for the members. Yeah. So for the bracings, we assign tension members. For the coupling members, we assign the member type truss, and the rest I can leave because the hinges for the upper coupling members I already assigned to the nodal links, and the same for the columns here. I don't have to assign an additional member hinge. Yeah, it would actually cause problems. I already have the hinge in my nodal links here. So my structure is properly connected, and I can again calculate the dead load case. Self weight is active, first order. I can run the calculation and can again double check the results. Yes. So again, deformations as expected. My axial forces in the beams. I have my bending moments again. So yeah, a comparable analytical file, this time created using nodal links and the IFC import versus the direct import from Revit. Yeah, maybe so far regarding the live demonstration. Now maybe a little view into the future. These nodal links won't be the last object that we implement. If you think of buildings with walls and slabs, yeah, concrete wall, concrete slab, and so on, then we also need options to connect them. This is what we currently develop and what we think of. So there will most likely be a line link in future to connect also walls and slabs, or to close those gaps that we would have there, and probably additional objects. And this workflow, after a little bit of optimization, should be an alternative to these direct interfaces. If we manage to have it, if we manage it to have it working quite well, then we would have automatically kind of a good interface to all CAD programs, because the an IFC file can be exported from any CAD program basically. And with that workflow, you can directly use the imported data. You can leave the beams where they are. Yeah. So the coupling members in the roof plane remain there where they are, yeah, on the right location. You don't have to move them around, which is also beneficial for a steel joint design in our add-on. Yeah, because if you want to have a steel joint for these coupling members and the main beam, you would have to define an eccentricity anyhow to place them here. So that's already done with this import. And an additional benefit from using the IFC format is the fact that when you import an IFC file and you convert it into a member or a surface, then the information from the IFC file will be saved in that object. As you can see it here, that is now the member that I edited. We have here a BIM tab with the information from the IFC file inside. And our plan is to also export this information again when exporting this file into an IFC. So that's of course also possible, exporting an IFC file from RVM. And let me show it. Yeah, here with the colors according to the section rendering. And yeah, the good part is because we save the information from the IFC file in our objects, we can also use them in our export again. So the exported IFC members have now the same GeoID that they had when we imported them from the IFC file. So basically this allows us, or all of us, a comparison of IFC files, because we have two IFC files, but the GeoID of the object is the same, which again allows this comparison. We can check the sections, the materials, and so on. And yeah, in future, we also want to extend the IFC export in general. We want to offer an export of our steel joints. We want to offer, or we want to implement the reinforcements export into our IFC format. So the goal is to have properly looking and properly looking IFC files from RFIM 6 with as many information as necessary. Yeah. And for that workflow, we want to use these nodal links and upcoming line links and maybe additional objects. Yeah. Okay. So far regarding the workflow and the information that I wanted to show today. From my side, I can only say thanks for the interest, and I hand it back to Andreas. Bye-bye.
Thank you, Lukas, for your nice presentation. I have a last additional hint. You can book our RFIM 6 course, for example, the course for beginners, or the Eurocode 2 course for the reinforced concrete design with RFIM 6, or the Eurocode 3 course for steel design. For more information, you can scan the QR codes or press the links at the bottom of the page here. You can download the slides from the same page as where you can find the recording. You will get an email in the next days with a link to the page with the recording and the webinar files. New is the Eurocode 5 course for timber design, and also new are the packages. Package number 1 for the Eurocode courses, and package number 2 for all courses. You can get the single courses for RFIM 6, Eurocode 2, 3, or 5 for free when you send us a nice project, and if we publish it on our website, you can get such a course or such a single course for free as a gift. Just send me an email and to info@bluebal.com, maybe with my name, Herold, in the salutation, and I will answer you and write you what I want to have for files, the pictures of the model or of the project, the model file for screenshots, and so on. It's not much work for you, I promise. Okay, that's also all from my side. I thank you for your attention. Thanks to Lukas for the presentation. Thanks to Paul for answering the question, or to help by answering the questions. I hope we meet each other in a future webinar. Bye-bye.